Hi everyone. Today we're going to look at section 6.5 and we're going to do a little bit of review of 6.4. I'm not going to go over 6.6. I didn't see anything on the common time exam for 6.6, so we can just kind of quickly go over 6.5. But I want to start off with a review of what we did in 6.4 because it's relevant to what we're going to do here. So we first looked at a bunch of different phase planes and kind of the solutions that came out of that. So we would kind of start a point on the phase plane to follow the arrows, and over time that solution would eventually just come to this point down at the equilibrium point there. We looked at a system that looked like this, where it would just go in a circle perpetually. We looked at a system where it had that same spiral shape to it. So maybe we start here, but then it started to spiral outwards from there. And just in general, we could talk about systems that kind of curve inward, right, and reach that point. And also systems that if you pick some point here, it would go over here. If you picked a point here, it would fly off in that direction. So we gave categories to these different phase planes. This one was asymptotically stable. And what that meant was this has a, as t goes to infinity, so as that asymptote goes to infinity, or as t goes to infinity, this asymptotically reaches that equilibrium point. So it eventually just settle down on that equilibrium point there. This one is also stable, but it's not asymptotically stable because as t goes to infinity, it doesn't reach that equilibrium point in the middle here. So for all these diagrams, we're assuming the equilibrium point is 0, 0 in the middle. But for this one, it's just stable. And the way you can kind of think about stability is that stability means you can draw a circle around it, right? Like if you start at some point and you trace the curve, you can kind of keep it inside of a bubble. So this one's inside of a bubble. This one, I draw a point here, I can draw it inside the bubble. But this one, however, if I use this as my starting point and start traversing that path as t increases, I'm going along this path of my solution. This one's unstable, and this one here is asymptotically stable. So the reason for that is any kind of point that I pick here, it's eventually going to reach that equilibrium point. So as t goes to infinity, it's just going to travel right to that equilibrium point. So this one's asymptotically stable. This one, however, is unstable. So the reason for that is if I pick a particular point here and let t go to infinity, it's going to fly off to infinity just like this one did. So we're going to say this one's unstable. Now, if you're given the phase plane, this is really easy, right? Like just figuring out what the what category it fits into based on the picture is pretty straightforward. And if you're not given a phase plane, you can maybe draw one. But there's an easier way. If you're given a system that looks like this, if you're given one of those y prime equals a times the y vector, where this is just a bunch of constants, right? So that's our A matrix. Then we can use theorem 6.3. And that was kind of another way to figure out which of these three categories the system falls into. By the way, this one, this is sometimes called a spiral. Theorem 6.3 says we can take information about the eigenvalues. Information about the eigenvalues, and use it to determine if something is stable or unstable, or asymptotically stable. So here's what the theorem of 6.3 says. So if you don't have a picture, you just have a system, then here's the rules. So if if all real parts of all eigenvalues are negative, then you kind of think of that as being, so you'd have something like, lambda equals -2 plus I, right? So that would have a negative real part. This imaginary part's positive, but the eigenvalue's got a negative part. This would turn into something like e to the -2t in the solution, right? And so you can think of this as t goes to infinity, this piece is going to keep shrinking. That's how we get this sort of shrinking behavior in here. So all the real parts of the eigenvalues are negative. That means that lambda is going to look something like this, and that means that we are looking at an asymptotically stable equilibrium point. The next option would be that if all eigenvalues are purely imaginary, so if all eigenvalues are purely imaginary, then that means we're looking at, well, something that is stable but not asymptotically stable. And that's kind of this situation. So if you have, for example, something that looks like a, so let's say lambda equals I. Right, so if lambda equals I, then your solution is going to look something like sine and cosine. So that's just going to be this situation where you're just kind of using polar coordinates to navigate around in a circle. The last possibility would be that at least one part of lambda is imaginary. And what that means, is let me just rewrite that. At least one real part of lambda is positive. So if at least one real part of lambda is positive, then that means that we're looking at an unstable system, right? Because that would just be like this, except it would be e to the 2t, and that would be kind of like a growing over time. All right, so as t increases, the radius gets bigger, the solutions get bigger, so that's just going to fly off to infinity. So this was 6.4, section 6.4. And that involved, either you're given a picture or you're given this thing here, and you could figure out information about the eigenvalues. But not every system looks like that, and 6.5 deals with a situation where we have not a system like this, but we're looking at a nonlinear system. So something that's a little bit more complicated than this. So we'll look at that at the next slide. So here's 6.5. So 6.5, this is about linearization. And linearization is this idea that if you're looking at the phase plane, and let's say here's your equilibrium point, so we're going to call that XE and YE are going to be the coordinates for that. And we're just going to kind of take some point that's arbitrarily close to that and figure out what's going on at that point. So we're going to call that Y. That's going to have coordinates X and Y. If we try to figure out what X prime and Y prime are at this point, think about what that's going to look like, what X prime and Y prime are going to look like here. If this is an equilibrium point, because if it's an equilibrium point, X prime and Y prime here are going to be equal to 0. So we can't really figure out what the solution is going to look like right here, because the solution is going to produce 0, 0 for X prime and Y prime. But here we might get some information about it. So the idea is that if we look at these previous examples here, the behavior really close to the equilibrium point tells us all we really need. Like, we don't need to know, can we trap this in a bubble? You know, that's more for like mathematically proving that something is stable, but we can just sort of look at what's happening near the, at some point near the equilibrium point. Like a solution here might look something like that. Might have some little solution that just kind of like dances around it. So anyway, that's what we're going to look at. Something near and dear to our hearts. Just a reminder, in this section, they kind of set up the system. Instead of saying y1 prime and y2 prime are equal to this and this, they call it x prime and y prime. And that's a convention that makes sense, because then we can call this the x-axis and call this the y-axis on our phase plane. And then these make more sense too, right? But the setup that we're going to use for this is we're going to call whatever this function is, we're going to call this one f of x and y, and we're going to call this one g of x and y. So these are just two functions. And in the interest of kind of keeping things short, I'm just going to say, using Taylor's series, we come up with the following formula. And I'll write the formula down in just a second, but I want to get across the point that these Taylor series are ways to figure out, or ways to approximate a function. So in this case, we're trying to approximate this function here. And we're trying to approximate that, and the way you do that is getting its first derivative, getting its second derivative, and using a formula for that. So that involves all the derivatives. We're just going to deal with the first couple of terms here. So using Taylor's series, we get the following. So if x prime is equal to f of xy, y prime is equal to g of x, and then these points are defined like this, then we get that our y prime vector is equal to del f del x del g del x del f del y del g del y. So these are partial derivatives, right, of these two functions. And then we multiply that not by just y vector, but this is going to be y minus this equilibrium vector. Before I go on, I do want to mention that this one, again, if we wanted to figure out what these values are at, we want to evaluate this at the equilibrium point. So that's what we're going to do. We're going to find these partial derivatives at x, e, y, e, the equilibrium point. So we'll find those partial derivatives, and then these are just the two vectors that I just pointed out here, right? This will become the y vector. I will say that your book will sometimes write this as, they'll say that this is the z vector. So they'll call it the z prime vector is equal to everything that I just wrote, del f, del x, del g, del x, del f, del y, del g, del y, times the z vector. I'm just kind of replacing this with z, replacing this with z prime. But this is still evaluated at, so I'll write it even another way, right? Evaluated at that equilibrium position. So this is the formula. Either of these forms are fine. Probably this one would be better to memorize. But let's go ahead and look at an example. And we'll kind of see that at the end of this, once we have this system out here, we're just going to get some numbers, right? Because this is evaluated at a point. So we'll get some numbers here, and then the eigenvalues of the numbers that end up in here, those are going to inform us. Whoops. Those are going to inform us on how we should proceed with this information here. Like we can use theorem 6.3 on the eigenvalues for this new setup and apply them to figure out if it's something that's stable, unstable, or asymptotically stable. Okay, so this is called the linearization. Right, this kind of this setup here. Right. So, like I said, let's look at an example of this. So we start off and it says x prime equals 1/2 1 minus 1/2 x minus 1/2 y times x, and y prime is equal to 1/3 1 minus 1/3 x minus 2/3 y times y. And this first one we call, right, so this is our f of xy in the formula, and this is our g of xy, and that's it, right? So this is really all we need here. I guess what I'll say here is if you, excuse me, false alarm. If you look at this, you might recognize it if you're in the 125 class. This is the example that Rick went over. So you might recognize that if you're looking for equilibrium solutions, remember that's where x prime is equal to 0 and y prime is equal to 0. And if you look at this equation, you can obviously, when x is equal to 0 and y is equal to 0, then you have an equilibrium solution, but you can also set this up to be equal to 0, these pieces here. So we'll first note that there's multiple equilibrium points. So there's multiple equilibrium points, and the system is nonlinear. So for this example, we're just going to look at one equilibrium point. So we're only going to look at 0, 0. Right? So just looking at the system, if I asked you to find the eigenvalues of this, that would be very, very difficult. Right? So we need to use, because it's nonlinear, so we're going to use linearization to come up with a easier to solve matrix, find its eigenvalues, and then look at if their real parts are positive or negative, and then go from there. So let's go ahead and do that. So we'll write down our formula. Right, z prime is equal to, well, let's go with the y version. So our y prime vector is equal to del f del x del g del x, oops, del f del y del g del y times our y vector minus our equilibrium. Again, just keep in mind that our equilibrium vector doesn't necessarily have to be 0, 0. We're going to look at 0, 0 here, but it could be 1, 1, 1, 2, right? There's other equilibrium points in here. And theorem 6.3 will still apply to those. So anyway, let's start figuring out what these pieces are. So del f del x del f del y del g del x and del g del y. Oops. So del f del x is going to be equal to, let's see. So we need to use the product rule here. All right, it's the partial derivative, so we're going to keep y as a constant. We're going to treat y as a constant and x like a variable. So I'm going to pull this 1/2 out and then do a product rule. So derivative of this piece with respect to x is going to be -1/2 times this piece, which is x. And then the next piece is going to be the derivative of this piece, which is 1 times this piece. So that's going to be 1 minus 1/2 x minus 1/2 y. Okay. I think since we're going to evaluate this at 0 anyways, we can just kind of leave it in this messy form. Let's see, del f del y. So that's going to be, let's see, 1/2 times x times y here. So we're treating y like a constant, or sorry, x like a constant. So x can come out in front here. And that's going to look like, I think, just -1/2, right? Let's see, del f del y, treating y like a constant. Oh, times 1/2, right? And then, yeah, I suppose these are all going to disappear, right? Okay, so I thought about it a little more, and we need to multiply this x out here. So the term that we'll get here is we're going to have that negative 1/2 here. This will be negative 1/2 times x. So when we take the derivative of this piece, the y goes away and we'll end up with an x here. So that's going to end up being the 1/2 comes from here, negative 1/2 x comes from these two pieces here. So that's going to be negative 1/4 x. This next one, del g del x, so that's going to be kind of the same situation here. Actually, no, this one's going to be easier, right? So this is going to be same situation. We have negative 1/3 x times y. That's the only term that's going to stick around. So this is going to be 1/3 times the negative 1/3 out in front times, let's see, so we're taking the derivative with respect to x, so the y is going to be what's left over. Okay, and let me just double check that I got that correct. This says I did it wrong, but I'm not really sure what the difference is. What did I do wrong here? 1/3 times anyway, del g del y, so that's going to be another product rule situation. So we've got 1/3 multiplied by, let's see, the derivative of this first piece with respect to y, so that's going to be negative 2/3 times y plus y times derivative, or sorry, yeah, what am I saying? The derivative of this piece times y plus 1 times the interior of this piece. That's going to be 1 minus 1/3 x minus 2/3 y. So that's a 1 there. Okay. So when we evaluate these pieces at 0, 0, we're going to get that this one is equal to 1/2. This one's equal to 0. This will say evaluated at the equilibrium, right? Evaluated at equilibrium, this one's going to be 0, and evaluated at equilibrium, this one's going to be 1/4. Sorry, I'm seeing now what the difference was. I copied down the problem wrong. This up here should be 1/4. So this is 1/2. Let's indicate that somehow, right? Okay. So let's see, that trickles down to, let's see, this is still going to be 0, this is still going to be 0, this is so 1/4 times that. So sorry about that. This one ends up being 1/4 down at the bottom when we evaluate it at that equilibrium point. So what we get for our equilibrium solution is that's going to come across right here, and so we get that y prime is equal to, so if we set these all up, we get 1/2, 0, 0, 1/4. And if we're looking for eigenvalues along here, if you have zeros along here, then you're basically just looking at your two, you're looking at the negatives of your two eigenvalues. So this is going to be y minus y at the equilibrium. But yeah, this is going to be very straightforward eigenvalues to figure out. So eigenvalue 1 in this case is going to be 1/2 and eigenvalue 2 is going to be 1/4, right? If you have zeros along here, then you're just looking at your two eigenvalues. So what this tells us is we have all real parts are positive. So if all real parts of the eigenvalues are positive, then we can say that this particular equilibrium point, 0, 0, is equal to, or has eigenvalues that are both positive. So that means that this is going to be unstable at this point, right? Like real parts mean that it's going to be growing over time. So this is an unstable equilibrium point. That's really it for 6.5. I do just want to quickly look at a couple of the other equilibrium solutions, just so you can kind of see how that's different on here. But basically, all that we're going to change, so I'll just draw these parts in orange here. If we're going to be looking at different equilibrium solutions. So 1, 1 is another equilibrium solution. If you plug in 1 to all these spots in here, then evaluating at this equilibrium point, you're just evaluating instead of at 1, 1, you're evaluating, or instead of 0, 0, you're evaluating at 1, 1. And let me think about what those points look like. So we have a little chart here. So that would produce, for this one, we'd get negative 1/4, and we would get df dy. So that would be negative 1/4 as well. This one, del g del x, is going to be negative 1/12. And this one here is going to be negative 1/6. So if you find that matrix, then you're going to end up with something that looks like, your matrix is going to look like this, right? It's going to be negative 1/4, negative 1/4, negative 1/12, negative 1/6, and then that is going to produce eigenvalues that look like, so eigenvalue 1, eigenvalue 2. First eigenvalue is going to be, well, it's going to be a conjugate pair. So this is negative 5/24 plus or minus something I, right? So the idea is that, so the eigenvalues here, I'll just write this a little cleaner. So it's got some imaginary part here. So negative 5/2 plus or minus some imaginary part. And the fact that the eigenvalue, the real part of it, is going to be negative on both of them, that means for this one that it's going to be asymptotically stable, right? So if we look at the previous information here, if all the real parts of lambda, are what happened here, are negative, then, which is the case with that orange example, then it's asymptotically stable. So that's it. This is just for nonlinear systems. We can use this formula. Either way, this is kind of your new A matrix here. But yeah, you basically find this, find the eigenvalues, use theorem 6.3, and that's section 6.5. So good luck with studying. You don't need to know anything beyond this. Just kind of be able to, if I give you a picture, if I give you this kind of system, if I give you this kind of system, be able to figure out whether the equilibrium points are stable or unstable or asymptotically stable. And then also know that this is called the linearization. So if you can write out, basically this is, x prime and y prime is equal to this matrix here, right? So this linearization is just a nice way to say that we're looking at, we kind of made our own z prime is equal to a times z. All right, good luck with the studying. I am working on getting through emails, so I'll have those up shortly.